Hi everyone, today I'm going to go through problem 1, just the proton NMR. I'm looking at the 13C NMR just yet. So we have 8 hydrogens and we have a possible structure. So this was our possible structure. We did the mass spec on it there last week. So this is butane 2-O. Now with NMR, proton NMR, you're looking at the hydrogens and you're looking at the environments. So we said we had 8 hydrogens. And what we see is we have 3 different environments. Now, this hydrogen, and this hydrogen are all within the same environment. They're all attached to that carbon, which is then attached to this. So that there is one environment. Now, if we look at this CH3, all those H's are attached to that one carbon, which is attached to that carbonyl. So they're all within the one environment. Now, note the differences between these two CH3s. They're very, very different. That CH3, or specifically the H's in that CH3, is attached to the CH2, whereas that there is attached to a carbonyl. So what's next to them is very important, and that determines their environment. And then we also have this CH2 here. These H's are both attached to the same carbon, which is attached to these. So these H's are in exactly the same environment. Now notice when we were talking about spin-spin coupling, which is down here, this happens because of the hydrogens in the neighbouring environment, or the hydrogens next door. So next door to the CH3 is the CH2. Next door to the CH2 is the CH3. But look what's next door to the CH3. It's a carbonyl. There's no hydrogens there. So I'm going to say here, no neighbours. No neighbours next door. And we'll come back to that in a wee minute, because that is not directly attached to another hydrogen environment. So if we look then at the spin-spin coupling, and this is directly from problem 1 in your spectra. I've just redrawn it here. Okay, so the first one here that you see is a quartet. This is a singlet. And this here is a triplet. So quartet, singlet, triplet. Now a quartet implies that there is a CH3 next to it. A singlet, remember, appears as an OH, but it also appears if there's no neighbours. And the triplet appears if there's a CH2 next to it. So that was the spin-spin coupling, but now we have to think of the integration, and I covered this the last day. And we wrote in 7, 12 and 11. So integration, you have 7, 12 and 11. Now, that tells us how many hydrogens are in each of them. So let's go and figure it out. We'll add 7 plus 12 plus 11. Okay, and what do we get? We get 10 and we get 30. Okay, we're going to divide that by 8. Why 8? Because there's 8 hydrogens in total. And I think that works out, what did we say? Was it, let's just check. Something like 3.8 per 1H atom. So every hydrogen atom is roughly about 3.8 millimeters. Now again, this is very, very rough. So if we take that there, the first one, our quartet, was 7 millimeters. So that would imply that there's 2 hydrogen atoms there. Okay, 12 millimeters, that would imply roughly 3 hydrogen atoms there. And your 11, again, very roughly, 3 hydrogen atoms there. And 3 plus 3 plus 2 equals 8. So let's link this back now to our possible structure. Does it verify our possible structure? Well, here we have a quartet. That means there's a CH3 next to it. And that implies that there's 2 hydrogens. So that quartet there is there. Now the next one then, we have a singlet, which we said has no neighbours, and there's 3 hydrogens in it. So that there is for that there. And our triplet then is a CH, implies there's CH2 to it, and there's 3 hydrogens. So here we have 3 hydrogens. There's a CH2 next to it. So we'll put a ring around that, and we'll go there. And that helps identify our final structure.